Hi everyone, it's Dr. Paul Kerstetter, and today I would like to talk about avoiding glitches in your FPGA design. Why are glitches a concern? They can cause unpredictable behavior or corrupted data. How to avoid glitches in Xilinx FPGAs, a strategy for glitch-free data, clocks, and resets in your digital design. Glitches occur when signals don't arrive at the same time within combinatorial logic. Even though the logic should produce a stable output for a given input combination, real hardware has propagation delays that momentarily create incorrect output values. In the example shown in the slide, input A is a constant logic 1 and does not change. Input B transitions from 0 to 1. Wire C is the inverted version of B, but because it passes through an inverter, it arrives later due to propagation delay. These unequal arrival times at the AND gate inputs cause the output on wire D to momentarily toggle, producing a glitch. Why are glitches a problem? For data paths, a glitch can be interpreted as a valid logic level by downstream combinatorial logic, or sampled incorrectly by a flip-flop, causing unpredictable behavior or corrupt data. For clock signals, a glitch on a clock line is especially dangerous because a flip-flop may interpret it as an unintended clock edge. This can trigger an extra data capture, violate setup and hold timing, or send the system into an invalid state. For reset signals, a brief glitch on a reset line can asynchronously reset part of the design, causing modules to restart unexpectedly or become misaligned with the rest of the system. Even very small glitches, sometimes only a fraction of a nanosecond, can be interpreted as meaningful events by flip-flops or asynchronous logic, leading to errors that are difficult to debug. Synchronous design solves most glitch-related problems because flip-flops sample signals only on clock edges, after combinatorial logic has settled. Brief glitches inside the logic are ignored as long as they occur between clock edges and timing requirements are met. This prevents unintended state changes, eliminates most race conditions, and ensures predictable hazard-free operation. In the slide, the data path is synchronous to the clock, illustrates this principle. However, synchronous design does not eliminate glitches on asynchronous signals or on sensitive inputs such as reset or clock pins, which still require special care. A common requirement in digital design is to operate a circuit on a fast clock and then switch it over to a slower one. However, if you simply use a regular multiplexer, like the one shown in the slide, to select between two clocks, you can introduce a glitch on the clock input of a flip-flop. Even a teeny glitch can be interpreted as an extra clock edge, causing incorrect data to be captured. So how do we safely switch between clocks in a design? To solve the clock switching problem, Xilinx provides a glitch-free clock switching primitive called BUFGCTRL. When switching clocks, if the currently selected clock transitions from high to low, after S0 and S1 change, the output remains low until the next selected clock also transitions from the high to low. Only then does the new clock begin driving the output. This ensures that no spurious pulses occur during the clock transitions, providing clean, predictable clock switching for synchronous designs. Key ways to avoid glitches on reset signals. Number 1, synchronize asynchronous resets on deassertion. Number 2, use only dedicated reset circuitry such as a register-based reset generator, a debouncer, a dedicated reset controller IP. Number 3, avoid combinatorial logic on the reset path. Even a single AND or OR can create a hazard if inputs change at different times. Keep the reset path pure by using direct routing synchronizers, one-hot finite state machine outputs, clocked logic instead of pure combinatorial resets. Okay, that's all for now. If you liked this video, please like it and subscribe to the channel. Stay safe and see you in the next video.